Welcome to the presentation of our paper, titled Lifelong Robot Library Learning, Bootstrapping Composable and Generalizable Skills for Embodied Control with Language Models. Most modern approaches for embodied control typically learn end-to-end policies with behavioral cloning. Even though increasingly more capable, such approaches still struggle out of distribution due to the absence of large-scale demonstration data. Additionally, their potential for lifelong learning is hindered by the effects of catastrophic forgetting. In the meantime, recent approaches utilize LLMs to translate natural language into executable robot policy code in zero-shot fashion. Policies are expressed as compositions of primitive robot skills, given by external vision and control APIs. Such approaches rely on careful prompt design and in-context examples to steer the LLM. However, the choice of the skills library and prompt examples remains a design choice that limits the span of tasks that the agent can tackle and require an expert to continuously adapt the library and prompts to the LLM. In order to tackle such limitations, we introduce LRLL, an LLM-based agent for lifelong robot library learning. LRLL continuously grows its repertoire of skills via interacting with its environment and users. This is achieved with the following contributions. First, we replace static prompts with retrieval from an experience memory. This allows dynamic context depending on the test instruction and ensures a fixed context window for the LLM. Second, we introduce an LLM-based exploration module, which proposes new tasks for the robot to complete in a simulator. The LLM suggests both new task variations that enrich the vocabulary of concepts the agent has experienced, as well as task compositions that expose the agent in novel combinations of skills. Third, we utilize an LLM to distill recently acquired experiences into new skills, expressed as Python functions factorized with the current library skills. This process exploits the code writing capabilities of modern LLMs to define functions out of example code snippets. Finally, we formalize a recipe for enabling humans to bootstrap new skills and guide exploration, which we call Wake-Sleep Library Learning from Human Guidance. Here we show an example wake-sleep cycle. At the beginning of the wake phase, the user introduces some general hints and a few demonstrations. Based on these, the exploration module proposes new tasks. Note that besides the policy code, which we call actor, we utilize a critic module to generate a success condition for the proposed task by exploiting privileged simulator data, such as contacts and object poses. This allows the agent to self-verify successful trials. During the sleep phase, we first cluster the acquired experiences based on their code structure. Clustered policies are fed as examples to the abstractor module, which then proposes new skills. A second round of abstraction generalizes the new skills across clusters, and the final skills are appended to the library. Then, the wake phase is replayed with refactored experiences, in order to compress the memory to the minimum number of experiences needed to express the new skills. LRLL continuously transfers knowledge from the human user, via the memory, to the skill library, relying solely on the in-context learning mode of LLMs. This allows complex skills to be formed from simpler ones over time, without utilizing gradients in any part of the process. We train LRLL in the blocks and bowls environment of the Raven suite, using a 4-cycle curriculum, including spatial coordination, visual reasoning, single object manipulation actions, and long horizon table-type rearrangement tasks. We find that in the lifelong setup, our method performs favorably versus end-to-end and static LLM baselines, while enabling higher generalization to novel attributes and unseen instructions. Please see our paper for further analysis and ablation study results. In this section, we illustrate that the learned skills can be directly employed in hardware. We replicate our curriculum in the Gazebo simulator, using a dual-arm robot setup with pre-trained vision model APIs and a catalog of household objects. We then transfer the acquired skills zero-shot in a real robot setup. Thank you for watching.